So today we're continuing on with the radiation, talking about nuclear transformations. And today we're going to discuss the radiation measurements and then the confusing array of units. Okay, it's not like measuring temperature. Well, temperature is, I mean, it's sort of confusing, right? You have Fahrenheit, Kelvin, Celsius. So there's 3 unit scales, but there's even more crazy unit scales for radiation. Okay, so, and these are units you've probably never heard of. Roentgens and Curies and Becquerels and Roentgen equivalent Mandos and Sieverts. And so it's a wide array of different units that we use for measuring radiation. And so this is how our detector works that we've been using in the lab. Let me just make sure I've got the video capturing. I have no faith in, yeah, okay, it's working. There we go. Okay, so this is how the Geiger-Müller tube or Geiger counter works that we've been using in the lab. It's we have a little rectangular box, but inside there is a tiny little tube. And there's a screen mesh and a mylar window. And so the radioactive particles are actually going through that thin plastic window and into this high voltage tube. And so there's a high potential between the cathode and anode and argon gas, because argon's pretty easy to ionize. So this particle comes flying through and ionizes the gas, and there's a voltage breakdown. And so it's a little lightning bolt, for lack of a better, more technical term. There's a little spark that happens in the tube, and then that sort of sweeps out all of the charge. The argon is back to neutral, the voltage is reestablished, and this can happen very quickly. But you see these little pulses, and a very simple way to detect that audibly is to have a speaker lined up in series with this. And so whenever that little lightning bolt happens, the speaker shakes and you hear it click. So the earlier ones just had a speaker lined up with this tube, and you could hear the clicking whenever you had a particle come through. Now it's all solid state. So the little circuit board is actually sending sound to the speaker. But in the old days, you just had a speaker hooked up to a high voltage tube, and you could walk around and you could hear clicks whenever there was radioactive particles coming in. And then you can also hook it to a counting circuit. And so that's what we have. We have a counting circuit. That circuit will make the speaker speak, because that's what you've always heard in the movies. You know, as you walk around, you hear all of the radioactive particles. And then that's a GM tube. So very sensitive, but also limited in its ability to count really high radiation counts. So I don't know if you noticed, but with the smoke detector, when you got really close, it may have said off scale, because this has to reestablish the high voltage before it can confidently count another particle. So there's an upper limit. And most detectors do have an upper limit, even visible detectors, like in our spectrometers. You can saturate the detector by putting too much light on it. And this same thing, if you're sending too many ionized particles in there that it can't reestablish the high voltage, it's going to miss a few. And so then the count is unreliable. So with the smoke detector at 0 distance, it's probably an unreliable measurement, because so many alpha particles or beta particles are going into the tube that there's essentially a current. Instead of voltage, it's just driving current through that argon gas, and you're not capturing independent counts. You're missing some. But if you back away a little bit, then you can count individual events. And so that thing, if you notice, it was counting up into the thousands. Mm-hmm. So that's a very fast refresh rate, meaning a particle comes through, there's a breakdown, then it's refreshed, and the voltage is reestablished, and then another particle comes down. It can do that thousands of times per second. So that's pretty nice, but it can't do it 100,000 times per second. Okay. They make different size tubes. You might be able to find a tube that's appropriately sized for such a high quantity of counts per second. And this is another way to measure it, scintillation. This is a fascinating effect. Radiation enters the sodium iodide crystal, shown here. And as the radiation slows down in that medium, it emits light. And the light little flashes, that's what the word scintillation means, flash. And so you see these little flashes of light. One little flash of light is pretty hard to detect, And so they hook this up to a photomultiplier tube, which amplifies the signal. So in the photomultiplier tube, you have an evacuated chamber, you have a negatively charged electrode, and then when that light hits that negatively charged electrode, an electron pops off and then goes through this cascade. These are more gradually more and more positively charged. And so this measuring device will measure this cascade of electrons. So it's easy for these photomultiplier tubes to give a billion electron signal for every flash of light. And they have a high refresh rate. So you can count very quickly in very high doses or very high activity of radiation. They make really large ones and really small ones. The smallest ones, are about this size. So you can have the little sodium iodide crystal in there and then a photomultiplier tube, and it's hooked to the counting device. So you see people walk around with the little, looks like an iron and the little thing. This is the photomultiplier tube, and you're using that. They even make these on what look like floor cleaners. And so it's the tube's facing down, and it's shielded on top, and it's a really heavy device. And so let's say we had a radioactive spill in this room, and we wanted to make sure it was clean. We would clean it all up, and then we would walk through the room with this floor detector, and it would detect any radiation on the floor. And if you're going along and you hit a patch, you go, okay, we got to clean that again. You back off, clean. Nothing. Okay, we're clean. So a very sensitive detector for detecting spilled contamination. That's the wonderful thing about it, is that radioactive contamination tells you it's there. I mean, I would take radioactive contamination over any other chemical contamination or biological contamination. I mean, because it emits light. You could spill arsenic in this room and never know it. You'd have to swab everything and run up to the GC, or not the GC, the ICP MS and see, and keep track of your locations. And we swabbed the whole room looking for arsenic, and we found it was here. Then you go back and clean. Think about the headache of having to run all of those indexed samples on an instrument to see where the arsenic was. Whereas if you spilled americium-241 in this room, man, all you need is a little Geiger tube. Okay, it's right here. Clean. Okay, it's gone. Drinking water contamination. Arsenic in my drinking water, same thing. Got to run it over to TRIS, put it through the ICP. Whereas here I can say, open the lid so it doesn't get shielded by the plastic. I'm not drinking that. And if it's click, it's down to background level. I mean, I'm going to get the same number of clicks here as I get here. I know there's a very little amount of contamination in there. So I like radioactivity. I mean, that sounds strange to say in this day and age, because people are so terrified of it. But I like when my contaminants tell me they're there with something as simple as a photomultiplier tube. So that's a slightly different view of things. Society has sort of panicked about all of this, and I don't know that it's justifiable. Okay, so here's some of the units in terms of radioactive decay. So if we want to just talk about the nucleus, how many disintegrations happen per second, then that would be the unit of becquerel. Okay. And that's almost not detectable, because you think about how many, our background radiation was, 13 counts per minute. Okay, 1 disintegration per second. Okay, that would be 60 disintegrations per second. But think about that. The products of that disintegration of a nucleus, and it could be beta decay, it could be alpha decay. So any of those decays send out 1 particle per second, and your detector's here, but that particle could go that way or down or sideways. It's a pretty low chance that it's going to hit your detector. So even though there's 60 disintegrations happening per second, the acceptance window of your detector is still pretty small. So that's going to be a pretty low level of activity. And so 1 disintegration per second is really low. And so 1 Curie is sort of a higher unit that's much more detectable, and it's 37 billion becquerels. Okay, so a Curie is pretty radioactive. So if you have something, if you have a source and it's, you know, a Curie in terms of its activity, you need to kind of stay away from that. That's pretty high. That's a 37 billion disintegrations per second. You know, send that out in a sphere, your small window of detection, that's still going to be a lot of activity on that spot because you've taken 37 billion and divided it by a sphere in terms of its, you know, what they call an angle of acceptance. So a lot of your sources, like if you have a calibrated source that you buy, it might say microcurie, you know, so 1/1,000,000th of that, so 1,000 disintegrations per second, 37,000. So that's a I would say a useful range. Our GM tube was calibrated to cesium that was running at like 1,000 disintegrations, I think. I'll have to go look that up. Okay, so then counts. Now notice disintegrations is based upon the nucleus. Counts is based upon the detector. So CPS or CPM, 1 CPS is 1 count per second. So that's how many disintegration or how many nuclear particles went into the detector. And our counts per minute is obvious. It's the detector counts per minute. And so that, in order to turn that into disintegrations, you have to know a lot about the geometry of the setup. And so it's pretty rare that we'll have a situation where we can get to disintegrations because we'd have to know the distance of the detector from the source material and, you know, what this solid angle is. We have to take into account the acceptance angle of the detector to get to how much the nuclei are doing. So rarely, only in sort of standards do we have this connection between disintegrations and counts. Most of the time we just have counts per second. And then those are that is the determination of how the detector is active. It doesn't necessarily mean dose, okay? So this one is where we start getting into exposure. So Röntgen, he's the scientist that actually discovered the X-rays generated by nuclear material. He put the uranium in a drawer with some photographic plates that were stored in the dark so that they, you know, you're getting ready to use your. That's how they detected light and X-rays and so on. They used photographic plates, and so he had these stored in the dark for future use. And he put some uranium ore in there, and then when he took the plates out, he saw the sort of the shape of this uranium ore, and he said, "Oh my goodness, this rock is emitting light because it exposed my film." So my film's ruined. What ruined my film? Well, he developed it, and he saw the outline of this rock. He's like, "That's crazy. I had this rock sitting on a photographic plate, and now my photographic plate's exposed." So that was Röntgen. And so then in his honor, they named this unit after him. This is an interesting, very scientific dose here. Microcoulomb per kilogram. So that's fantastic. That's actually telling you how many coulombs of charge have been deposited per kilogram of body mass. Okay, so if you get hit with a gamma ray and it goes right through your body and doesn't generate any charge, then you didn't receive any dose. Were you exposed to gamma ray? Not really. It went through your body and didn't do anything. So there's no detectable exposure. But this one is pretty difficult to measure as well because you've got to know exactly how much of the ionizable radiation was distributed or deposited in the body mass. Okay, and so it's pretty rare to be used. We have a Röntgen equivalent. So you take the radiation that you're dealing with, whether it's beta particles, or alpha particles, or gamma rays, and you'll divide that by some factor that will make it relevant to a sack of water, because that's what we are, is a sack of water. So that gets into this REM, or Röntgen equivalent. And so this is, and we have dose multipliers for this biological effect. So for X-rays, gamma rays, and beta radiation, this dose multiplier is 1. So if we were to eat an active substance that was emitting beta particles, whatever its activity would be used to calculate our dose. But if we ate an alpha emitter, like if you ate that smoke detector, you would take its activity and you would multiply by 20. Because the alpha particles generate enormous damage to tissue. And so it's 20 times the effect. Now, some of these are just sort of safety rules of thumb that they use, but this is in calculating if you were to ingest an alpha emitter, you would take that activity of that alpha emitter if you were able to figure out what it was, and you would multiply by 20 for biological damage. And then this is sort of meeting halfway. If you don't know what it is, like you ate a radioactive substance, we don't know what it is, we're going to take its activity and we're going to multiply by 10 in terms of its biological effect. And then that's how we're going to calculate the Röntgen equivalent man dose. It's the rads. So this is energy deposited per gram or joules, per kilogram. And an erg is a CGS system. Do you remember that? We covered this once. Shall I review?
Ergonomics?
Yeah, that's where ergonomics comes from. So what are the units on a joule? Yeah, so let's go up here. So kilogram meter squared per second squared. Okay, and so that's the MKS system. Meters, kilograms, seconds. So MKS system, we use joule. CGS is another system. Okay, erg is equal to gram centimeter squared per second squared. So centimeter, gram, second. So it's the same, it's energy, okay, but it's just using as our base units centimeters and grams instead of kilograms and meters.
Kind of scaled down.
Yeah. So it's sort of two competing units, but we know ergonomics that comes from this energy sort of looking at the energy required to do your job and how you sit and how you stand. It's sort of energy analysis of the body. And then also, whenever we talk about exothermic and endothermic, we're talking about enthalpy. Okay, but when we talk about spontaneity, we talk about Gibbs free energy, and a negative Gibbs free energy is exergonic, and positive Gibbs energy is endergonic. So we're talking about energy going in or coming out, and so we still use the word erg occasionally, and that's where it shows up. So up here, 1 rad is 100 ergs per gram.
When it comes to to know doctors when they work with x-rays and stuff like that, they're only limited to a certain amount of time per a time frame exposure. Is that because after a certain amount of time you have so much exposure that it's...
Yeah, and that's in today's notes. So we'll go,
Okay.
So today's notes we'll talk about that, and then next set will be medical effects. And so we'll look at what happens in the body and also the medical uses for radioactive isotopes. So then we have this energy that's deposited in the body per kilogram of the body or per gram of the body, and so not all of the radiation we're hit with is absorbed. That's the bottom line. Mostly it's the gamma rays that go through. The beta rays and alpha particles are captured by the body. So this is how we get to the unit rem. And now they weren't happy at leaving it alone, and so now they've added the dose of sievert. So I don't know who sievert was, but now we've gone from rems to sieverts. And so 1 sievert is 100 rem. And so whenever I was forced to add this into the notes, because I grew up with rem. Everything was rem or millirem. And then they had the Fukushima reactor kind of scramble in Japan after the tsunami and earthquakes, and everything in the news was written in sieverts. And I'm sitting there reading the news, I'm like, what the heck is a sievert? Come on, And so I had to go to the calibration myself just to read the news articles, and so then I put it in the notes. And it's not a 10 to the 3, which we're used to, right? We're used to just moving the decimal place by 3. It's 100, which is goofy to me. It drives me crazy. So anyway, I've put the sieverts in the notes, and then our tube, our little vernier, vernier science calculator, for our detector for radiation will give you counts per minute, okay? And that's good, that's detector counts per minute, but it also does dose. So when you guys were converting counts per minute to dose, this is the calibration that you were using. So they were saying, essentially this radiation monitor that we have in the lab is measuring the radioactivity of the Fiesta plate and the smoke detector as if it were cesium-137. So that's an assumption that's built into that detector. But those aren't cesium-137. Now, in terms of the activity and the types of radiation that they emit, it's an okay assumption. But you just need to know that if you were dealing with something completely exotic, a really high energy emitter or something like that, then that assumption might not be very valid. But this is a good, safe assumption that we can use. So we could have flipped the little switch on that detector. Instead of going counts per minute, we could have flipped it to millirem per hour. Okay, and so all those calculations that you had to do for the lab to try to figure out what our dose would be and extrapolate it to a 2,000-hour work year could have been done right with the tube in millirem per hour, and then you could just add it up. And so, sorry, but you needed to know how to do the math behind that, And so, I gave you this calibration in the lab handout. So 1,000 counts per minute is equal to 1 millirem per hour. But that's what are you smiling about?
I calculated it as if you were like fully exposed for 1 year.
Yes.
So I did 8,760 hours.
Oh, really?
So
Yeah.
it was kind of like no way you would be near it.
Yes. And so, so the work week, I found that out too, sort of a generic human resources work year is 2,000 hours. So if you're going to try to fund a full-time position, that's the number you use to kind of come up with your budget. And so that's it's not related to PChem, but if you're ever doing estimates of what it costs to pay somebody full-time for a year, 2,000 hours is a generic sort of 8-hour workday with a couple of weeks vacation. And so let's talk now about the kinetics of radioactive decay. And this is absolutely beautiful because it's first order kinetics, like the easiest kinetics that they have. No second order, no autocatalytic business, none of this other crazy stuff they do in biochem. So it's just very simple first order kinetics. And so we learned in chapter 14 of the freshman text, I'm sure you remember, the first order processes obey these equations. And so this is nice. Spontaneous nuclear transmutations are first order processes. And they will say, and this is kind of an odd thing, there's nothing you can do to change the kinetics of nuclear disintegration. That's not exactly true. Okay. You can hit it with a neutron, you can hit it with a gamma ray, you can have nuclear collisions and cause these rates to change. Right? That's how we get nuclear power. Because the normal decay rate is X, but if we hit it with neutrons, we can spontaneously, or we can stimulate nuclear fission. So if we didn't have stimulated nuclear fission, if this were true, we wouldn't have stimulated nuclear fission. So we're actually changing the fission rate by hitting it with neutrons. Does this make sense? Otherwise, it would just be spontaneous nuclear decay, and we wouldn't get as much energy out. We can actually hit it with neutrons. It's called neutron activation. And it's actually a spectroscopy. Most elements will have some response to neutron activation. So if I were to spray all your elements with neutrons, they would emit characteristic gamma rays or other kinds of particles, and I could put detectors around there to measure those energies, and I could get your whole body atomic percent. So every trace element in your body would give off its characteristic signal, and you integrate all those crazy peaks, and you get the atomic percent. And neutrons go through any material. So this is a way to get the atomic percent inside the dense container. In fact, this would really be great if you could spray neutrons on a truck to see if it had any nuclear material inside. And we do that. So for Homeland Security, you got a shipping container, comes along, you got a neutron source, and you're looking for uranium, plutonium, strontium, all these radionuclides, And you say, oh, wait, we've got something fishy in this container. It says it's filled with gummy bears, but why are we detecting uranium? You know, so yeah, so there's a problem, you know. Anyway, that's sort of a side trip on this. Spontaneous nuclear transmutations are first order processes without any other kind of nuclear event taking place. Yes. And then A and AT represent the activity in counts per second. So this is also a very useful substitution. So you have this nuclear decay constant, and I like to think in terms of half-lives, and so this is the conversion of that rate constant or decay constant into half-life. And so here's an example that we use. So kinetics of radioactive decay, we can use this to date objects. And so a wooden object from an archaeological site is subjected to radiocarbon dating. What does that mean? Well, we take that sample and put it in a spectrometer and measure its disintegration rate related to carbon-14. And it comes out to be 11.6 disintegrations per second. And then the activity of an equal mass of fresh wood is put in there, and it measures 15.2 disintegrations per second. And we know the half-life of carbon-14 is 57.15. So what's the estimated age of this archaeological sample? So we could take this, convert the half-life into our rate constant, and then we have the fresh wood activity rate, which would be A0, the archaeological activity, AT, and then we solve for T. So we get 2,233 years. So that would be the age of this archaeological object.
It's a lot simpler than I thought it would be.
Yeah, it's so straightforward, yeah. But what are we assuming? So think about this problem, look at all of the things that go into it, and tell me what we're assuming. Let's pull a thread on this and see what the assumptions are.
So we only have the first order radiation.
Yeah, so we're assuming first order, which is a safe assumption because we're not hitting this carbon-14 with neutrons or gamma rays. You know, you have to intentionally mess with the system to change that first order. So it's a safe assumption that it's first order kinetics.
The only thing we're radiating is carbon-14?
Okay, very good. The only thing that we're detecting would be carbon-14. Now, you could check that assumption by detecting the gamma rays that come off and looking at the characteristic energy of those gamma rays. And so you could say, all right, carbon-14 typically gives a gamma ray in this energy range. And so you could say, yeah, we're confident that this is carbon-14 that we're detecting.
Okay.
But that would be a way to check it to see if there was some impurity in there, like potassium-40 or thorium or some other kind of radioactive element in that archaeological sample. So that would be a good question to ask. Are we sure this is carbon-14 that we're dating? Okay. But that's a good thing to pull, a good thread to pull. There's another few assumptions in here.
You're using fresh wood versus super dated wood?
Yes. That's probably the most vulnerable assumption, is that fresh wood is our activity at year 0. See, how do you get a, this is activity at time t, 11.6, and activity at time 0 is 15.2. And so you're assuming that the fresh wood is representative of the fresh wood 2,000 years ago. You see that? Now, it may be a decent assumption, it may not be. Where does carbon-14 come from? This is a new slide. So if you've got the notes, this is not in there. So where does carbon-14 come from? You can draw this on a new sheet of paper if you want. There's a large amount of nitrogen in the atmosphere. Nitrogen's isotope, nitrogen-14. You know, it's the most abundant nitrogen isotope, and it's almost 100% nitrogen-14. So there's N2 gas in the atmosphere, and it's being bombarded by solar wind, and some of that solar and light from the sun too. Vacuum UV, so deep UV light, can split apart not just the triple bond of nitrogen, you know, the 2 double bonds, but also the sigma bond. So regular old UV light that's close to visible will only really interact with double bonds, you know, the homo-lumo gap. But then once you get higher energy, then you can start exciting the sigma bonds. And we call that vacuum UV because it's absorbed by sigma bonds and tightly held double bonds like in nitrogen. So in order to use that spectroscopy in the lab, we have to pull a vacuum on the spectrometer, because just nitrogen gas would absorb that. But in the atmosphere, we're not going to evacuate the atmosphere, right? So this vacuum UV comes through the vacuum of space and gets into the atmosphere and is absorbed by nitrogen. And it splits apart the diatomic molecule into single atoms. And then those single atoms go higher into the atmosphere and they become ionized, and that's what we call the ionosphere. So way out the outer reaches of our atmosphere is called the ionosphere. And it's the ionosphere because the sun is ionizing those atoms. So way up there, then you have cosmic rays, higher energy, either protons, neutrons, things that are spewing out of our sun, hit that nitrogen nucleus and excite it. And so that nitrogen nucleus is excited, and one of the possible processes of that excited, that little star means this is an excited nitrogen-14 nucleus. It can spit out a positron and become carbon-14. And so now at the outer edges of our atmosphere, we have carbon-14. And our atmosphere is reactive. It's oxygen. It's got a lot of oxygen. It's an oxidizing atmosphere, and you know carbon will react with oxygen. So then that carbon-14 becomes carbon-14 CO2, and then through respiration gets captured in the Earth's biosphere. So this is a steady state process, meaning if the concentration of nitrogen in the atmosphere doesn't change and the solar wind doesn't change substantially, then we'll have a steady state of CO2 in the atmosphere that's carbon-14 and a steady state of carbon-14 in the biosphere. So this is the connection of carbon-14 in plants. And as long as they're respiring, they're capturing carbon-14 CO2. It decays, but they respire and capture some more. So plants will be in contact with this atmospheric process until they stop respiring. And so when a plant stops respiring, then you have a fixed amount of carbon-14 and it begins to decay. So that's the whole basis for carbon-14 dating. Now, this is not the only radioactive dating method. There's potassium-40, which works on a similar process. You have argon in the atmosphere. Mm-hmm. Argon gets excited. Have you ever noticed? It's kind of strange. Look at argon, 39.948. The potassium, 39.0983. It's kind of weird, but I mean, essentially they're the same mass. And so you can go from argon 40 to potassium 40 through one of these radioactive methods, and then potassium 40 is radioactive. So we have carbon 14 in our body if we eat salad, okay, or if we eat animals that eat salad. So all the carbon that we have in our bodies also is got carbon 14 in it. So we're radioactive from carbon 14. We eat bananas. They always say bananas are high in potassium. Okay, so all of our food is high in potassium. But anyway, so we have potassium 40 in our bodies, which is radioactive. In fact, if you are living with somebody, you have a higher radioactive dose than if you're single, because we're radioactive. Yeah, it's not a risk, but I'm just saying that's a fact. You know, if we're radioactive and we spend our time with somebody, we are radiating each other. This is a weird fact. It's not important, but it is. So anyway, that's just and so then you could do potassium 40, and then all of these other elements that are in the Earth's crust, uranium and thorium and plutonium and all kinds of things are radioactive. Now, some of these have quite long half-lives, like thorium-232, 14 billion years, and uranium, 4.5 billion years, uranium-235. You know, it's still got a long half-life, but it's a lot more radioactive than uranium-238, right? It's only 700 million years. Plutonium, very radioactive, 24,000 years compared to the elements that it comes from. And then carbon-14, 5,000, cesium and strontium, 30, and iodine-131, 8 days. Yeah. So I ask you, which one of these is most dangerous?
The 131 iodine.
It's interesting. You immediately want to go to the shortest half-life. Why would that not be the most dangerous? There's two reasons.
Because it does happen
Is
sometimes.
it's gone, yeah.
Yeah,
So it'd be
it's
hard to get a decent dose of it because it's decaying so fast.
Yeah.
So that's one reason why it's less dangerous than some of the others. The second reason is iodine is a halogen salt, a stable anion, and you pee it out. Okay, so it doesn't stay in the body, right? It's water soluble, and so if you get exposed to it, drink a lot of water and flush it out of your system.
Okay.
Yeah. So where is iodine collected though? It's sort of sequestered in the body. There's one place in particular where iodine is sequestered, held on the thyroid. Yeah. And so they'll give people iodine 131 and do a thyroid scan. It's sequestered or captured by the thyroid, and then your thyroid lights up. And if it's the correct shape, then they're like, okay, you're good. If it's got a bulge here or a bulge there, then you've got some kind of thyroid disease. And so they'll use iodine 131 medicinally to scan the thyroid. But which one of these on here? There's one that's moderately radioactive. So this row here is bad. Now, which of these two is more dangerous?
Well, the detector detected cesium, so maybe that.
But let's say they both have the same detectability and they're very active. So they're both 30 years.
What's the difference between them?
What's the significant difference chemically, not nuclearly, chemically between cesium and strontium?
It's reactivity with water.
Oh, well, yeah, I guess solubility. Is that what you're kind of
Maybe
going with?
cesium could be a
Well,
salt.
also this isn't like solid cesium explosive.
Oh, we're not talking about the pure metals. We're talking about the ions. So cesium cation versus strontium cation. There's a significant difference between the two. Just work your way up those two groups. What do you find? Because these are chemical groups. So thinking chemically, they're going to behave like everything else in that group chemically. So like the second column, the alkali earths are all not soluble with sulfate. So you could precipitate this out with sulfate, like you could barium, right? But there's another important thing in these columns that tells you why strontium and cesium would behave differently in the body.
Oh.
So I don't know if this, like what you're getting at is like enzymes and like gradients, but like I think a lot of stuff like sodium and potassium is more towards like gradients across membranes, whereas like magnesium and calcium are more like enzyme centers. I don't know if
You're on the right track. You're on the right
Yes,
track.
yes.
So enzyme activity would be different between these two for sure. There's another major issue that even if you didn't have any biochemical experience at all, you would know that this difference is important for the body. Y'all don't have kids yet, but what do they want you to tell kids all the time? That's a weird question.
Yeah, don't reminisce the
Yeah.
thing.
Eat your vegetables, and there's one other.
Drink your milk.
Boom!
What? Why?
Why?
What?
Your body treats strontium like calcium.
Yes, and what does it do to calcium?
Deposit in bones.
Yeah, and that doesn't going to leave you, is it?
Oh.
Oh, so it's strong.
I wish I'd recorded that. That was like the teacher's dream. Oh, yeah, that's the most dangerous effect. Is strontium 90 getting stuck in your bones.
Would that also work in your nerve ends?
I don't know much about that.
Okay.
Yeah, but yeah,
I
you
know
need
what you're talking
calcium
about.
for
I don't think
neurotransmission.
so.
Because
But-
lead does the same. Like lead replaces like calcium, and that like causes like nerve damage.
Oh, interesting. Yeah, no, I mean, there may be the case, but I'm just thinking about getting stuck in your body for 30 years. If that's the half-life, I mean, you're going to get all of that. That strontium's going to sit in your bones until it emits. And what's it going to be destroying? Your bone marrow. You're going to get leukemia.
So how
You're
would
going to
you treat
get
that?
blood cancer.
I don't think you do.
How would you get rid of the?
Replacement therapy. You have to, if it's immediate, like you just got exposed to strontium-90. Like there was a dirty bomb or something. This drives me crazy with my keys. Sorry. You just got exposed to strontium-90. You're going to flood your system with calcium, and you're going to drink EDTA like it's nobody's business. So you want to deplete your body of metals without killing you, and you're going to try to replace it with a multivitamin and calcium. So you're just trying to use Le Chatelier's principle to keep it from getting stuck in your bones. But the toxin is the dose. I mean, if you get a dose of strontium-90, you're going to be in trouble.
Are there any like known sources? Like, what ways are people contaminated?
They're not really. So this would be the most disastrous effect of a dirty bomb. So they use strontium-90 in some applications. I think it's either this one or cobalt-60 for irradiating spices. So if you think about a spice, it's sitting on your shelf for how long? Forever, right? You want that to be sterile. You want to sterilize those spices. And so you have a plant that's grinding up oregano, sticking it in a bottle, shooting it down the thing, and you run it into this room, and this highly radioactive source comes up, and we're kind of getting into the next lecture of uses of radioactivity. You irradiate the crap out of those spices and kill everything biological in that bottle. And so there's no bacteria, no mold, no mildew, nothing living inside that bottle. And then you just sit on a shelf for decades. Now don't sneeze in your spice bottle because... And so this is an example problem of 7 half-lives, but really you can just use 10. And so like if strontium-90 was blasted out into New York City, essentially it would be an area denial for up to 300 years because of a 30-year half-life. So you have to wash down the buildings and collect that runoff and, store it in Nevada or something like that. Sorry, Nevada. It's going to be around for a long time, and it's really dangerous. So that'd be the most nightmare scenario is if somebody got a lot of strontium-90 and stuck it around an explosive and then blew that up, it would disperse strontium-90 around, and that would be one of the most damaging radioactive materials to disperse. The thing that destroys its effectiveness is you want to disperse it over a large area to have a big effect, but by dispersing it over a large area, you've reduced the dose. And so the toxin is the dose, and so that's kind of working against the person who wants to cause havoc, because the more you disperse it, the lower the dose. And so that works to our advantage. That's great. I'm more afraid of biological weapons than I am of these kinds of things, but still they could wreak havoc and deny you an area. We live in an ionizational, radioactive world, and we're basing everything on the energy to ionize water. We're sacks of water. I mean, I know we're more than that, but at least we're that. And so if it can ionize water, it can create biological damage. And so that's the cutoff. And you can convert 1,200 kilojoules per mole, and you get to about 100 nanometers. So light below 100 nanometers, that includes X-rays and all of these other things, is ionizing radiation. So everything's radiation. Even infrared light is radiation. But it's not ionizing radiation, and so that's the word we use. And next time we'll get into the biological effects. So here's the detectable of clinical effects is got a threshold. And if we're below that, we don't detect any radiation damage at all. So, see you next time.